Hi everyone. Today I would like to talk about matrix multiplication. So this is a general version of matrix vector product, a scalar times vector, a scalar matrix product, and um, the dot product, actually, the inner product of the, two vectors. So the goal of this video is to know how to calculate the matrix multiplication, and more importantly, get an intuitive understanding of matrix multiplication. Remember when I was talking about the matrix vector product, I said that one way to understand or to visualize the matrix vector product is to consider as a linear combination of the columns of matrix. Let's say A, when you A multiply A by X is a linear combination of columns of A, right? So it was like this. We had AX, and then this one is interpreted as X1, A1, X2, A2, all the way to Xn, An, where A is like A1, A2, all the way to An, right? So that's a very intuitive way to understand the matrix vector product. We want to do the same thing for matrix multiplication. So here's the setup. I have a matrix A with m rows and p columns, which is m by p. Matrix B has a p rows and n columns, which is p by n. So when you multiply them together, you get the m by n matrix C. Okay, and the elements is defined as Cij. So this is the matrix C that I have here, which is m by n. Now, what is Cij? Cij is calculated using the ith row of A and the jth column of B, right? And that's what this expression said. It says Cij is equal to sigma k from 1 to p aik times bkj, where k is changing from 1 to p. Why? Because A has p rows, p columns, sorry, and B has p rows, right? So if you plug it for different value of the k, you will see that this is equal to ai1, the first column of A, and the ith row of AI1, ith row and the first column of A. So it's going to be somewhere this one, this element, right? It's going to be multiplied by B1J. B1J means first row of B and the jth column of B, this one. So this multiplied by this plus the second column of A and the ith row of A again, this one, multiplied by the second row of B and the jth column. So if you keep doing this and add them up, you get the Cij element, where I is changing from 1 to m, of course, because I is the index of the rows of A. And remember, A was m by p, has m rows, and J is going from 1 to p, right? Why? Because, so J should go from actually 1 to n, right? Why? Because B is p by n. So P has actually n columns, okay? And K is changing from 1 to P because A has P columns or B has P rows, okay? Now, before talking about the properties, in order to multiply two matrices, the dimension should kind of match. What I mean by match means that if you are multiplying A times B and get the C, right? If A is m by n, then B should have the same number of rows as the number of columns of A. So this should be n, and then the number of columns of B can be anything. Let's say, for example, I don't know, K. In that case, C is gonna be, these two are the same, it's gonna be m by K, okay? So number of rows of B should be equal to number of columns of A. Otherwise, you cannot multiply them together. Okay, now let's talk about the properties. The first property, order matters. What I mean by that? So A, B in general is not equal to BA, this expression. In general, they are not the same, right? But if you want to compare AB and BA, if you want to have a meaningful comparison, A and B, both of them should be square matrices, okay? Otherwise, either of them do not make any sense, one of them at least. For example, let's say A is m by n and B is n by k, where n is not the same as m is not the same as k. Okay, let's see. So what happens to AB? AB is going to be n by k, so we have no problem with this. But what about BA, right? Let's see. So we are going to multiply n by k matrix by m by n. But guess what? If you multiply them together, the k and m should be equal. Why? Because the number of rows of A should be equal to the number of columns of B, right? So m should be equal to k. Okay, so m should be equal to k in order for them to actually make any sense, right? So in order for the matrix AB and BA to be compared even with each other, to have any meaningful comparison, A and B, both of them should be square matrices. But the important thing to remember is that A, B is not in general equal to BA, so order matters. Okay, the next one is associativity. What I mean by that is, let's say you want to calculate the product of three matrices, A, B, C, right? You can first multiply A and B together and then find the result, let's say is equal to D, and then multiply that by C. So that's what this expression says. You can group A and B first together and then multiply the result by C. Or you can go ahead and multiply the second two, this one, and then multiply the A from the left by BC. Remember, the order matters. You cannot switch the left and right places with each other. So first you can multiply B and C, find the result, store it in another variable D, and multiply A by the variable or by matrix D. You can do that. You can extend this one also to the concept of multiplication by a scalar, of course. So this gamma is a scalar here. Now, gamma AB, you can multiply gamma anyhow you like, right? You can first group it with A, you get another matrix, right? You multiply this gamma by every single component of A. You get one matrix, and then you multiply B by that. Or you can actually group that with B, right? And multiply the result by A. You can also do this. Distribution with addition, meaning that if you have A times B plus C, you can go ahead and multiply A by B first, and then add it with A times C. So you can do this one first, and then you can go ahead and do the A times C next. Okay. Transpose of product. This is pretty interesting property. When you are calculating a transpose of matrix product, what you get is that you will switch the order of two matrices, but then before switching the order, you transpose both of the matrices. What I mean by that is that, let's say that you have matrix A and B. You want to calculate AB transpose, right? This B comes first with the transpose first, and then A comes next. It comes B transpose, A transpose. The same thing applies for the inverse, interestingly enough, right? So if you have AB inverse, right? Of course, AB inverse, in order to make any sense, if you have watched the video for the inverses, right? In order to make any sense, this means that AB should be invertible. This means that A times B should be a square matrix, right? So this one is the same thing. To become B inverse, A inverse. Okay, great. Now let's go for an intuitive understanding of matrix-matrix product. This is very important. So assume matrix A is a n by p, and matrix B is a p by n matrix. Okay. Now define A to be n by p matrix, and it generates n by p. Now represent B as a column representation of. Remember, we could represent any matrix, let's say B, in two different forms. One of them was like this: B1 transpose, B2 transpose, as a block row representation, right? BP transpose as P rows, or we could represent as a block column representation, B1, B2, and Bn, because it has n columns. Okay, so here we are look at the column representation of matrix B. It turns out if you do that, when you multiply A to the B from the left side, you are going to go actually multiply A by every single column of B. This is very interesting property. This means that the column of AB, the column of the product of A and B, is equal to product of A and columns of matrix B. But why is this correct? Why is this actually correct? Let's take a look at this one. Let's take a look at why this one is actually correct. So if you write the matrix A as let's leave matrix A as it is, right? As a very generic matrix A, right? As this form, A1 transpose, A2 transpose, a row representation, all the way, how many rows? AM transpose. And matrix B as column representation. Let's see what we get here. B1, B2, and Bn. Okay. When you do AB product, what you do actually is that for the first row of AB, what is the first row of AB? The first row of AB is coming from the first row of A multiplied by the first column of B, then second column of B, and all the way to the nth column of B. So we're gonna get the first row of A, which is A1 transpose, times the first column of B, then second column of B, all the way to nth column of B. Okay, good. Well, then what is the second column of, second row of AB? The same thing. First row of A, second row of A, sorry, times the first column of B, and the same thing is for mth row. It's gonna be transpose B1, all the AM transpose B, and okay. Now, if you look at this one, if you carefully look at this result, you will see something very, very, very interesting. What is the first column of this AB? This is AB. What is the first column? The first column has B1 in common among all of them. Well, what is it? The one that is multiplied by that is A1 transpose, A2 transpose, all the way to AM transpose. But wait, what is that? That's just matrix A. So the first column of AB is the matrix A multiplied by the first column of B. The second column of AB, look at that, the B2 is the same among all of them. But then we have A1 transpose, A2 transpose, all the way to AM transpose. So that one is equal to matrix A multiplied by the second column of the B. And hence the expression that we have here. It's a very, very interesting expression. Okay, so this is called the column representation or column interpretation of the matrix product. Now let's take a look at the row interpretation of the matrix product. So remember, for a matrix vector product, the row interpretation was not that intuitive. It still was useful. Maybe you can use it as some form of whether the vector X is orthogonal to rows of matrix A, right? And then sometimes, for example, we will be dealing with the null spaces. Then that would be a good intuition to have it as a row representation of the matrix A when you multiply X. But in general, the column representation is more useful. Here also the same thing is true. The column representation is more intuitive than the row representation. Well, now let's see what is the row representation of the matrix product. So the same way I explained, assume the rows of A are A1 transpose, A2 transpose, all the way to AN transpose. Okay, so this is a row representation of matrix A. Now it turns out that AB is nothing but A1 transpose B, A2 transpose B, all the way to AM transpose B. What it means is that you're gonna go ahead and multiply each row by the matrix B, right? So the first row of AB is gonna be the first row of A multiplied by the entire matrix B. And the same way for the second row and all the way to the mth row, right? If you want to look at this again, the proof is very easy. Always consider the B as written as a column representation, and then go ahead and multiply AB together. If you do that, what you end up with is this. So in order to calculate this matrix product, you multiply this by this, A1 transpose B1, then A1 transpose B2. This is all gonna be for the first row, right? And then this one by this is gonna be for mth row. You will fill out this, right? Now, if you take a look at this one closely, now look at this one. Very much look at the first row here. You see that the A1 transpose is the same. So you can factor from A1 transpose here, and you will get what? B1, B2, all the way to Bn. But wait, what is this? What is this B1, B2, all the way to Bn? This B1, B2, they are columns of A, columns of B. This is nothing but matrix B. So it's going to be B1 transpose B. If you look at the second rows of AB, again, you factor from A2 transpose, you get what? You get B1, B2, all the way to Bn. This is going to be A2 transpose times matrix B, and all the way to AM transpose times matrix B. So what it says is that each row of AB, the product of A and B, is equal to the multiplication of each row of A times the matrix B, right? So remember, A1 transpose is gonna be a row vector because it's a row of B, each row of A, and then B is a matrix. So the result is gonna be a vector. That's why it's gonna be the first row, right? This is gonna be the second row, and all the way it's gonna be the nth row. Okay, so that's two ways to look at the matrix product, which both ways are actually important. The column representation is the one that we use it more often to intuitively understand the matrix product. Okay, so that's it for this video. See you all in the next video.